Log on, tune in, find out. Another good idea from Cambridge.
Okay. Okay. So, yeah. It's a pleasure to have Ling Bao, who will talk to us about gauge theory duality from M theory and the topological vertex. Very much.
So first I would like to thank the organizers for inviting me here to this very nice workshop. It has been lots of nice discussions and talks. So the work that I would like to talk about is done in collaboration with these fellow postdocs, Eli Pomoni, Masato Taki, and Futoshi Yagi. So my starting point, so first an outline. So I will first introduce the background and go directly to the results that we found. And then after that, I will go through the derivation of this result, first by some motivation and then provide two different derivations. And then I will end with a discussion. So first to the background. So the starting point of this work is n equals to 2, four-dimensional n equals to 2 SUN linear quiver gauge theory, which can be written using a quiver diagram with m-1 SUN gauge groups. So the bifundamental hypermultiplets are charged under the gauge groups, or the gauge symmetry groups. And in addition, we are in the superconformal case, which means that there are two global symmetries, which also are SUN. So for notational convenience, we choose to, so on this side we had the fundamental hypermultiplets, and on the other side anti-fundamental ones. So this gauge theory is very well known to be realized into A3 theory using the Hernani-Witten setup. So we have n NS5 branes, which goes like this, and then between two NS5 branes there is a stack of n D4 branes due to the fact that we have SUN gauge theory. So for the global symmetries, we have in additional n flavor D4 branes on the right, and also n flavor D4 branes on the left. So these branes are not stacked. There are n single D4 branes, which means that we have a mass deformation. So going to the Coulomb phase, all the stacked D4 branes are turned into n single D4 branes. So again, these are NS5 branes, all the horizontal lines are D4 branes. So this system was first solved by Seiber and Witten in 1994 in terms of a Seiber-Witten curve and a Seiber-Witten one form. At that time, the Seiber-Witten curve described auxiliary complex Riemannian manifold, but later it was realized that this thing can be written as one single M5 brane instead of, by uplifting to M theory. So before continuing, I will just count the number of degrees of freedom for this system. So there are m-1 UV coupling constants, which are the ones, all the distances between the NS5 branes. There are n fundamental masses, which are the ones on the right, and also there are n anti-fundamental masses, the ones that are on the left. And also there are m-2 bifundamental masses that goes between the, between the D4 branes that are here and the D4 branes that are here, for instance, across NS5 brane. And also there are Coulomb moduli, which corresponds to all the single D4 branes that are in the middle. So this is a very well-known story. So this theory can be uplifted to 5 dimensions to what is called n equals to 1 SUN gauge theory, living on the space-time, which is the original four-dimensional space, times a S1 compact circle. So our result is that we explored a duality that is between gauge series with SUN to the power of m minus 1 gauge group with, if you swap n with m, so the dual gauge group is SUM to the power of m minus 1, and I will explain why this is so. So what we did was to find a duality map between the gauge theory parameters, that is the UV coupling constants, the flavor masses, the bifundamental masses, and the Coulomb moduli of the two series. And from there, we assume that by finding the map, we assume that the IR coupling constants are equal to each other. So this duality has been mentioned before in the literature, both in the context of geometric engineering, Calabi-Yau compactification, and also by looking at this brane configuration as well. So, but what we did here was that we found the explicit map, which has, so as far as we looked, haven't found. So there are several motivations for why this. Yes.
Is there just a purely four-dimensional counterpart of this statement?
Exactly. So that is one of the things that we would like to know, whether it can be pushed towards 4 dimensions.
Oh, I see. So at least in your story today, it's important that you are in 5 dimensions.
Right. Exactly.
I see.
Right. So the motivation for this duality is that so we are staying on the Coulomb branch for the entire talk. So the gauge symmetry in the Coulomb branch is broken from SUN to actually U1, and it's the same gauge group, if you like, in low energies, both on this side and on the dual side. So this is the first thing you would see, that actually the gauge symmetry is the same. And next, we could count the number of physical parameters for the two series to see whether there could be actually written down a map between the two. So actually, I already counted the parameters for you a few slides before. So the first line denotes the gauge coupling constants, the UV ones. And the second line are the fundamental and anti-fundamental masses. So the third line is the bifundamental masses, and the fourth line are the Coulomb moduli. So the total number is n plus 1 times m plus 1 minus 3. So since the way n and m appear really symmetric here, swapping n and m gives you exactly the same number here. But you could also do the exact counting, and then you see that you end up with the same number. So at least the number of physical parameters are the same, so it gives you a hope to find a map between them. So one of the real, or the first time we saw this duality was mentioned was given in this Katz-Meyer and Waffa paper, where they didn't talk about this duality in the context of a brane setup, but they were in the context of a Calabi-Yau compactification. So in order to get this gauge theory, you need to compactify on toric Calabi-Yau in order to get SUN gauge group. So this Calabi-Yau manifolds can be written as a fibration with AN minus 1 singularity, fibered over a base which is S2. So the way the Calabi-Yau manifold is written, you could see from the equations there that there's a symmetry between the fiber and the base. So these authors argued that you could actually exchange the base and the fiber, leading to a duality between SUN to the power of n minus 1 with SUM to the power of n minus 1. So this is the first argument based on geometric engineering. So the second one was given in the same year by Harani and Cole, where they started from the branes configuration in the 2A string theory. So my indices are denoted such that alpha goes from 1 to n, where n is SUN, and I goes from 1 to m, which is the number of gauge groups. So this is again the same picture as I had before with NS5 branes, all of them, and the D4 branes that are horizontal ones. So my Coulomb moduli parameters are numbered from down to up. So this is 1, 1, and so this is a general A alpha I, and this is n. So it counts the number of D4 branes. So having this picture, so the usual four-dimensional picture is that you have here, so the gauge theory, four-dimensional gauge theory lives on x0, x1, x2, and x3. So here x10 is the M-series circle, so the D4 branes has one more extension, which is in x6, and in addition, the NS5 brane is living on x4. So the configuration that we have is that we say that instead of being infinite direction, x5 is actually a compact circle. So this has been argued by Washington Taylor that if you have D4 branes, which in string theory with a target space having a compact circles, it is at least with one compact circle, it is just like a five-dimensional gauge theory. If you have D compact circles, then you have 4 plus D dimensional gauge theory. So having this target space with x4 like this, x6 like this, and the two compact circles indicates that we can actually rotate this picture or do a reflection so that the role of NS5 branes and the D4 branes get exchanged. So this is the uplift to M theory where I have drawn an M5 brane. So here again, these vertical lines are the NS5 branes. These horizontal ones are D4 branes, but these together, I mean, one should view the entire thing as one M5 brane. So here are the X5 circle that we introduced, and also this is the M series circle. So we can reflect the picture, for instance, along the diagonal, which means that I'm exchanging X4 direction with X6, and also exchanging the cycles X10 with X5. This would swap what was called NS5 brane before and what was called D4 brane before. But from the M series point of view, it's just one M5 brane, so there's really not much difference. So the M theory, the M5 brane description of this D equals to 5 SUN gauge theory has the geometry with a four-dimensional space times the Seiberg-Witten curve. So this is six-dimensional in total. So the Seiberg-Witten curve is a complex polynomial written in terms of two complex variables. And using this relation, you project out two of the directions. So you actually end up with a Riemannian surface, Riemann surface. So this is a polynomial in the two coordinates, complex coordinates, as I said. One is what we call W, which is exponential of x4 plus x5. So just to remind you the directions. x4 is the one that is along the NS5 brane, and x5 is the compact circle which NS5 brane is wrapped. So T is the corresponding one.
Yeah,
Yes.
I'm sort of confused. So
Yeah.
when I write down M4 cross Seiberg-Witten curve, normally I would think that's describing a four-dimensional theory.
Sure. Yes, it's the n equals to 2 gauge theory.
Here you say it's d equals 5. So I'm a bit confused about the number of dimensions I'm in.
Does it depend
okay.
on
It's
how
a-
your Riemann
okay.
surface
The
is?
reason is because this variable now is a circular one. So the usual d equals to 4 theory has this t variable,
Yeah.
but the other variable is x4 plus I x5, not
Okay.
exponential. So the fact that I'm using a periodic coordinate here means that I'm ending up with a 5-dimensional theory.
This Seiberg-Witten curve is some Riemann surface on which
Yes.
the M5 is being wrapped.
Right.
Now you can degenerate this Riemann surface in one way such that part of it is very small and you can take a degeneration limit, I imagine, where you can go to 5 dimensions in 2 different ways. So that's your duality, right?
Yes.
But you can also take the whole thing small, in which
yes,
case
exactly,
you go to 4
precisely.
dimensions.
Right.
So it's different
Exactly.
limits of the same
I
system.
see.
Yeah, exactly.
Mhm.
So in one case, you take this one to be infinite, and in the other case, you take this one.
Yeah,
So, yeah.
I'm happy.
Okay. So the number of exponents here for the polynomial is depending, of course, on the SUN gauge group and also the number of gauge groups. So all the physical gauge theory parameters are inside these C coefficients. So all the parameters that are denoted with a tilde are 5-dimensional parameters. So these are also periodic, if you like. So yeah. So other than the Seiberg-Witten curve, we also need the Seiberg-Witten form, which is a meromorphic differential, and this one is obtained by looking at the volume form of the M2 branes, which are ending on the M5 branes. So from this meromorphic differential, it is possible to find the unique holomorphic differential for this Riemann surface.
It seems that all the formulas you wrote above
Yeah.
is more or less, almost
Exactly the same, except for that I'm changing one of the variables.
Yeah, but with the Seiberg-Witten form,
Yeah, so this one is it's slightly different. So in one case, it's you have so we have 2 logarithms here. So for the usual one, you only have 1 logarithm. The other one is what is written on the exponential, so to speak.
the
So it's all these formulas are really almost like in the 4-dimensional case. So the Coulomb moduli again are, as usual, defined as cyclointegrals of the Seiberg-Witten form around the A cycles of this Riemann surface, and the prepotential are obtained by taking the cyclointegral around the B cycles. So from the prepotential, you can define the action of this gauge theory. So basically, all this is motivation that you just need to check the Seiberg-Witten curve, for instance, if you want to see the duality for the 2 series. So in this language, the duality corresponding to this SUN to the power n-1 and this SUM to the power n-1 just correspond to swapping W with T in the Seiberg-Witten curve. So doing this on the curve, we see that the only thing we need to do is to read off the coefficients and identify them with each other. So these guys are written with the dual inside, and I have to exchange the indices k with L. So this procedure is really straightforward. So now we need to have the explicit form of the Seiberg-Witten curve for this theory. This can be done by looking at the asymptotic behavior of the branes. At least it can be partially defined, found explicitly. So the asymptotic values of the D4 branes are what we set down from the beginning, it's M1, M2, M3, and M4 that are the 4 flavor masses. For the NS5 branes, these ones, one could solve or minimize the NS5 brane world volume by solving this Laplace equation. And they only give, so you solve this separately for one NS5 brane at a time. So I'm doing this before I forgot. So I'm doing here the SU2 self-duality case, just an SN illustration. So solving this equation, you will find the solutions that the NS5 branes stretches to infinity and take these values. So since there are 2 equations to integrate here, there are 2 integration constants. One is called C, and the other one we call it CQ. So the reason we call it Q here is because when you actually take the product of this one and this value, this becomes the average of the NS5 brane position for this NS5 brane, and you can do the same for this one. And then you take the distance between these 2 averages and you get the number Q. So this Q indeed is the naive, what you naively would think is the gauge coupling constant, because the gauge coupling constant should be the distance between these 2 lines, NS5 branes. So the Seiberg-Witten curve itself, since this is, we are in the SU2 case, it's a degree 2 polynomial in W and also a degree 2 polynomial in T. So by taking into account the asymptotic values of these guys, so both these ones and also these ones, we find the Seiberg-Witten curve to be of this form. So almost everything is determined in terms of the gauge theory parameters that are the masses and also the A's, which are the Coulomb moduli. What is not, so there is one constant, the C here, that is so far not determined, but it will be fixed once we fix the normalization of the coordinates. So Q is, I have already briefly explained, should be the coupling constant. And what is not determined is this part B. So this one should be related to the gauge, the Coulomb moduli, but the relation is very complicated, so this we never determined for the curve. But it will not be very important to find the map. I mean, in principle, we could also find the map for the Coulomb moduli using the transformation of the B, but we choose to do a simpler way. So this curve, various limits of this curve have previously been given. So in the weak coupling limit, it was given in these papers. And in the R5 goes to 0 limit, which is a 4-dimensional limit, you just keep the 0 modes and remove all the massive modes. It's of course given in the original Seiberg-Witten paper and also later on in some other papers. So the fact that the masses appear very simply in this form, you can just go ahead and exchange T and a W, and you get very nice duality relations for the flavor masses from the Seiberg-Witten curve. So for the duality relation of the Coulomb moduli, in principle you could do it implicitly from the transformation of this B. But to determine B in terms of A is really complicated, so we choose to actually compute the contour integral of the Seiberg-Witten one form instead. So looking again at this M5 brane picture, one could go take the contour integral around each of these 4 junctions. So if I concentrate on this one, the integral going around up here and down here, up and down, should be vanishing. So it actually gives me relations between the poles that I pick up by doing the control integrals along each of these lengths. So this one is the Coulomb moduli, and this is what would be called the dual Coulomb moduli after doing the reflection. So the relation I get in the end is very simple for the Coulomb moduli themselves. So this one M1D is actually just this value. So as I promised before, this constant C in the Seiberg-Witten curve can be removed, not removed, but fixed by setting the conventions. So the conventions we choose are A1 corresponding to this line, with A2 corresponding to this line. So the product of these should be equal to 1. So this is just one of the conventions. I mean, you can choose any. And this uniquely fixes this parameter C. So in the end, we find this quite simple duality map for the SU2 self-duality case. So the masses are dualized. So the dual masses are a combination of the original masses with the coupling constant. So the dual of the flavor masses do not depend on the Coulomb moduli parameter. So this can be generalized quite easily to SUN case.
In this SU2 example, what's the limit of? So let's see. So in one duality, in one theory, you can take the 4-dimensional limit in one theory, and you can.
You can also do the. So in one case you are expanding x5. In the other case you're expanding x10. I mean, it's two 4-dimensional series in some sense. So in some sense it's a 4-dimensional duality, but it's not. Yeah.
Is it a strong weak coupling duality? Or?
In some sense, yes, he would say so. Maybe, yes. I might comment on this later on, so I will see. So by going to SUN case, you just mimic the method that was used for SU2. So you compute the asymptotics for your branes, and then you get the Seiberg-Witten curve, and also you compute all the cycle integrals around each junction you have. So in the end, we find a duality map in this closed form. So here there are the integration constants, C, and so now you have a number of Q's because you have several gauge groups. So this C is can be fixed by setting the normalizing your coordinates properly. So the conventions we choose are for the flavor masses. We put the product of the flavor masses equal to 1. So the notation I'm using here is that when the index, the upper index for A is 0, then it's it's flavor masses, and the same goes for M. So I didn't introduce separate flavor masses in this case. So everything is called A. Although those ones that are in the middle are actually Coulomb moduli, and the ones that are on the side are actually flavor masses. So this is finding the duality map using the Seiberg-Witten curve. So we know that there's a separate way to describe this Seiberg-Witten solution using the Nekrasov partition function. And this function is you start from the 4-dimensional one, which has so you start from your 4-dimensional gauge theory, which has Q, some M, and some Coulomb moduli, and then you deform your theory using 3 variables. So one is called the beta, and then you have epsilon 1 and epsilon 2. So epsilon 1 and epsilon 2 are what is called omega background. And this beta can be interpreted as keeping beta finite means that you actually is in d equals to 5 theory. So by looking at, so the Nekrasov partition function is actually 5-dimensional by itself. So this partition function has two pieces. One is perturbative, and the other one is the instanton sum. The perturbative part contains tree level and one loop contributions, and the instanton sum is infinite sum of all the instantons. So we'll concentrate on this instanton part. So already in the original paper, Nekrasov said that this partition function should be equivalent to the field theory limit of a topological string amplitude on some Calabi-Yau manifold. So already before I mentioned that an equivalent way to see n equals to 2 gauge series in 4 dimensions is to do Calabi-Yau compactification. So this gives you n equals to 2 supersymmetry, and in order to get SUN gauge symmetry, this Calabi-Yau should be some an minus 1 fibration over S2. So Calabi-Yau manifolds with this form are toric ones, or are called, they belong to the toric category. And toric Calabi-Yau manifolds are characterized by toric web diagram. So from now on, I will drop the name web and just call them toric diagrams. Toric diagram can be computed. The toric diagram can be obtained from this brane picture by taking a T-duality. And then you uplift to the 2B picture. So actually, the toric, when you think of the toric picture, then you're actually in 2B case. Although what you started with is the 2A picture. So I can give you roughly the way to compute the string amplitude using this topological vertex formalism, but the computations themselves are quite complicated and technical. So roughly the instanton partition function is given by the way to compute it is very similar to compute Feynman diagrams. So for each vertex, so you should compute the contributions from the vertices and also the lines. So from each internal lines, so these 4 ones, you assign them with a parameter which we call large Q, and you also, for each of them, you assign a set of all the Young diagrams. So when you sum here, you should sum over all the Young diagrams that are these are also internal lines, of course. So you should sum over all the Young diagrams that are corresponding to these internal lines. For the external ones, they are attached with empty Young diagrams. So it's a singlets that you put on the outer legs. The 3 vertex, the contribution of the 3 vertex was computed in this paper, and it contains mathematical functions which are called Shor functions and the skew Shor functions. So there are a whole list of different identities that you can write down for these guys. While from the internal lines, which are the propagators, the contribution depends on this parameter Q, which is attached to each of these lines, and also something that is called a framing factor, which depends on something that typically people call it a small q, which is this beta is the radius. So it's the same beta as this guy here, and h bar is when you put epsilon 1, so these parameters, epsilons, you put epsilon 1 equal to epsilon minus epsilon 2 equal to h bar. So in this case, I will just concentrate on the usual topological vertex by restricting to this subset. So you could do general epsilon 1 and epsilon 2 by using something called the refined topological vertex, but it's the computations are much harder, let's say. So
Large Q is the stochastic for instant numbers.
No, I think these ones are the.
Small Q is just H bar.
Yeah, so these ones will be related to the gauge theory parameters in the end.
Yeah, that's the stochastic.
Yeah, yeah, okay. Yes, sorry. So to compute the, so to write down according the topological vertex amplitude is very straightforward by using this rule. So you just write down everything that are, so you write down contributions from all the vertices and all the lines. But the difficulty lies that in order to compare this amplitude with Nekrasov's partition function, you need to compute some of the sums explicitly, because in order to relate these parameters to the gauge theory parameters. So for this diagram, for instance, there are two. So you should sum over all the Young diagrams that correspond to this line, this line, this line, this line, this line, and this line, and then leaving the y1 and the y2 unsummed, and then you will automatically land on the Nekrasov partition function. So the way we did it was to compute this part by itself, and then sum over this part separately, and then glue them together in the end. So now, after you actually computed the sums, you can compare with the Nekrasov partition function, and you see that, so what I called QM1, which are these 45 degrees lines, they are related to the flavor masses, M1, M2, M3, and M4, and also the QF, which are this distance, or this line, it's related precisely to the Coulomb moduli, which from the brane picture is the distance between the D4 branes. So QB is, these lines are just some combinations of everything. And it's related to the coupling constant. So the coupling constant is, again, as intuitively said, the distance between the NS5 branes. So now the duality that I talked about before is just doing a reflection again on the toric diagram. And all the symmetries in particular, so the way the toric diagram is, so the topological vertex amplitude is computed up here by using this algorithm. It shows that the duality is manifest for the topological vertex. So basically, you just sum over. So instead of choosing do not sum over these two lines, you can choose to leave these two lines free, and this precisely corresponds to the Nekrasov partition function for the dual theory. So for instance, so I choose the reflection. So the QB is swapped with QF, and also the M2 and the QM3 are exchanged like this. So now again, you can rewrite. So these are in the language of the topological vertex formalism. So using what we have found here, we can rewrite this duality in terms of the gauge theory parameters. And these correspond exactly to those that we found before, using the Seiber-Witten curve. So, but now we have shown that these two theories really have identical partition functions. So now you can do slightly more work by generalizing. Yes.
Before going to
Yeah.
you say that, I mean, by doing this different kind of division, you should be obtaining the same expression, but is that rigorously proven in the topological vertex context?
No, it's the same expression from the start. So you just sum over different parts.
Yeah, but
It's you start from the same expression before you start to sum, so it's automatically the same. You don't take any limits or anything. It's automatic.
renaming parameters depending on which field you're
Yes, exactly. So you could say it's just a renaming, of course, as well. You could say it's just remaining on this level. So really, from the topological vertex, so once you have written down the toric diagram, this duality is manifest. The only work that is there to do is to do the mapping with Nekrasov partition function variables. So now you can do slightly harder work by generalizing this. So, but the philosophy is really the same. So what we did was to sum along these lines separately. So for each of them, we did a subdiagram summing all this, and then glue everything together.
So once you write everything into this PQ diagram things, there's nothing else you should do.
Right, exactly. So in terms of the Qs, it's really manifest, yes. So what is not manifest is maybe writing the duality map in terms of the gauge theory parameters. So so now the sum takes a bit more energy to do, but in the end you can do that. And comparing with the Nekrasov partition function, so the QMs are related to the A tildes divided, it's quotes like this. And the QB is again proportional to the coupling constant. And all these ones are in fact not independent variables. So there are lots of Qs, but they are not independent. You can show you can show an independent set consists of only m plus 1 times m plus 1 minus 3 number of variables. And these are exactly the same number as the gauge theory parameters. So the duality map, as I said, for the reflection symmetry is exchanging QF with QB. And also exchanging this index on the QMs. So QM has two indices, and so you're exchanging these two guys, more or less. So again, written using this mapping with the Nekrasov partition function, we could show that this duality is exactly the same as the Cyber-Witten, as from the analysis before. So now I will just comment very briefly on. So at this point, this is our main result. Where we show yes.
Just going back to this SU2 self-dual example, we don't have to go back, but it's just SU2 theory with 4 fundamental flavors, so we should be having larger duality than S-duality-like thing, SL20 subgroup.
Yeah, sure. So I think that the reason that so we just checked the duality where we exchanged X5 cycle with X10. So this is, you have a torus there, so in principle you should have, we checked very little on this, but it looks like the Cyber-Witten curve, for instance, looks a bit strange. So when you actually do a transformation that goes from, so you could do, for instance, T goes to WA TB, and then W goes to WC and a TB, something like this. And then, so it looks like you are not conformal anymore. So when you write down the Cyber-Witten curve, it looks like that you are not really conformal. So we're not sure exactly what it means.
What do you mean you're not conformal?
So for instance, because, so in the conformal case is that if you look at the Cyber-Witten curve, there's the polynomial for the T and for W should be of some value, and it should have this kind of form that you have the masses, so W minus all the masses times some certain power of your T here. So once you actually do this kind of, you start to change the powers of your polynomial. So the number you get here, it looks a bit strange. It doesn't look like.
But anyway, in your original theory already, before performing this duality, you break conformal symmetry by expectation value and advances, right? Non-conformal to start with.
Yes, but all right. Yes, Sure.
Yeah, but I just wanted to ask, I mean,
Yeah.
general, extending that kind of idea for
Yes.
SU2, I mean, going back to your general cases with M
At
and
least,
N,
okay,
whether
yes.
you're generating some new theory by doing this SU2.
Yes. So anyway, so we checked this kind of, but we were not really able to say anything. I mean, concluding about that. There are guesses, but it's dangerous to say guesses. All right. So just ask.
Can you include
yes.
some operators into your duality, like Wilson lines, or is it just a partition function which they are the same? Or
So it's so we just check on the level partition function. So.
but
we
do you
don't-
expect any observables you can turn on?
Sorry.
Do you expect any observables like Wilson lines, etc.?
Uh,
Trying to make any correspondence? Do you expect such correspondence to hold, or
Are you saying whether we can go beyond the IR fixed point? Or?
not really? We can just
Okay.
take gauge theory and include Wilson line, for example.
Yeah, maybe Wilson and Tooth lines could be dual to each other because from type to B, it really looks like S duality.
Yeah, that's why I'm asking partly, but I see.
Okay.
Greater move the brain.
Okay.
Yeah.
Mhm. Okay. I see. So
Okay.
probably it's more straightforward.
So just a comment in the end before, in the context of the AGT conjecture. So the AGT conjecture was that if you start with the M5 brane dynamics, that is a 2,0 superconformal field theory on this some four-dimensional space, which is having this omega background deformation, times a Riemann surface, you could compactify on either the four-dimensional space, so you land on a conformal two-dimensional Liouville theory, which is identical to if you would compactify on this two-dimensional Riemann surface, so that you end up with a four-dimensional n equals to 2 gauge theory. So by extending SU2 case to the SUM case, this Liouville theory gets extended to the so-called Toda series. And then by uplifting to this five-dimensional case, you have to introduce some Q-deformed Toda theory on the Riemann surface here. So since our duality we checked is on this corner, so if the five-dimensional AGT conjecture is true, then our duality would mean that there is a duality between on this side as well. So between m+2 point functions of Wn algebra and m+2 point functions of Wm algebra. So the duality that we have checked could be a way to explore the five-dimensional AGT conjecture. So the five-dimensional AGT conjecture has been previously proposed already, so it is probable that it is true. So the ending remarks. So in this work we have looked at a duality map between five-dimensional n equals to 1 SUN to the power of m minus 1 gauge theory with SUM to the power of n minus 1 gauge theory, where you exchange n and m. Future directions would be, for instance, as I already mentioned, to look at the five-dimensional AGTW conjecture. And since not very much is known for Q-deformed Toda series, this duality would be a new way to look for m-point functions for this Q-deformed Toda series. And also, as already been asked, the four-dimensional version of this duality. So the only comment I can make is that on the level Seiberg-Witten curve, Nekrasov has given a coordinate transformation of the parameters from the 5-dimensional Seiberg-Witten curve to the 4-dimensional one. So that coordinate transformation is exact. So this means that there might be this duality, the fact that we are shown for the 5-dimensional case, using his map, this duality might exist for the 4-dimensional theory as well. So another interesting direction would be to go beyond the infrared fixed point to look at the index, for instance. And also, so this AGT story, or AGTW story, can be also rephrased using the matrix models. So for n equals to 2 gauge series, there has been 2 matrix models that have been proposed. One is where people try to look at n equals to 1 gauge series by deforming n equals to 2. So this one was proposed a long time ago. And then there was a new one which was proposed in the context of AGTW. And so far, no one really knows what the relation between these 2 matrix models are, although they describe the same theory. So it could be that using this duality, we might find some kind of relation there. And of course, extending. So in this talk, I only look at the case where epsilon 1 is equal to minus epsilon 2. So extending to generic omega background would also be possible by using the refined topological string partition functions. Although, yeah, so thanks for listening.
Did you make any progress for the last one, or for the direction, especially?
Not really, yes. So there's several differences comparing to the usual topological vertex formalism, because for the refined ones you have this preferred direction. So this was the fact that it looks very symmetrical was kind of used in our derivation of the to show the duality. But there is this conjecture that saying even if you have to have, so even if you have this preferred direction, after you sum over everything, so you get the partition function, it doesn't depend on this preferred direction. So, I mean, the hope is that it works there as well. So, but we haven't actually done any computations there. So, yeah.
What is this theory? Oh,
Sorry?
so when you put the theory on the Nekrasov-Chapter background,
Yes,
in other
exactly.
words, actually one of the epsilon parameters vanishes.
Right, exactly.
It corresponds to the quantum integral system.
Right, exactly.
But once you have different theory, you end up with 2 different integral systems. Then do you know how this gauge theory duality
Not
can
really.
realize in this?
Not really. But yes, so Nekrasov-Chapter's video limit would also be something to look at. I agree.
Question, sorry, but you're saying that you're mapping the topological vertex, I mean parameters in the topological vertex, partition function, and the Nekrasov one.
Yeah.
I think all the field theory parameters. You said you identify the 2 parameters by comparing the 2 expressions. Nekrasov's expression.
Yes, exactly.
Apparently looking very different.
No, after you do the sums, they look the same. So
But do you have a complete analytic control and show that the 2 expressions are really the same?
yes.
Not expanding.
Yeah. It's exactly. So what you use is that you use all the summation rules for the Schur functions. So everything is
Both
controlled.
general, these M and N.
Yeah, everything is controlled very well. So there's no ambiguity over there. So no limits are taken ever.
Usually the only feeling I got about this topological vertex because it looks horribly complicated.
Yeah, the computations are very complicated.
They have complete analytic control.
Yes,
Relatedness.
yes.
Okay.
I mean, all the yes. So all the relations you use are mathematically, I mean, there are relations between the Schur functions, how you do the sums, so it's well proven.
Is there anything special about the particular P
Yes.
diagram you used, which allows you to
Yes, I mean, you could, yes, so there are several ways to write down this diagram, of course. So you can do this, yes, so the way, if you start with a particular symmetric way, then your computation is easier. So, but in principle, it should not depend. I mean, it's just, so when you write down this diagram, it means that you just, you don't sum over these horizontal lines. But if you do another diagram which is equivalent to this one, then you have to be more careful how to do the summations, because you want to end up with exactly the same expression as Necker's partition function. So it could be that, yeah. So it's a bit of trial and error, but if you start with this kind of symmetric ones, then it's easier.
Anyone else? Yes, let's see. Speaker testing.